Dear world, welcome back to the next session of trees. So in first lesson we have observed the basic concept of trees, the architecture and about all the nodes and the important terminologies of trees we have understood. So this concept has already been discussed. In today's section we'll be understanding the types of trees. All the type of trees that we'll be understanding in today's section one by one in depth. So let's start without wasting further time. We have already understood all those things of the slides. So we'll start from the types of trees. First of all, we are talking about trees. So trees is like this. It is having a genuine like this type of architecture or structure. So let's say this is 1 and this is 2. This is 3. Again, these are having nodes 4, 5. So those are child nodes. So this is what we call a tree. So now we'll be talking about a lot of various type of trees. So first let's understand the binary tree. As marked here, what is binary tree? So a tree is binary tree when it is having at most two children. Just mark the word binary. Mark the word binary. What do you understand from this word binary? Binary, that means either 0 or 1. That means the value is 2. So whenever our tree will have at most two childrens, at most two childrens, then we call it the binary tree. Then we call that binary tree. So the binary tree can have either 0 or it can have 1 or it can have 2 So let's see what can be the examples of binary tree. Let's see. If you call it this is a tree with node 3, we call it binary tree. Yes, this is binary tree. Now if you call it this one 2 3 4 5, observe. So we can call this one also binary tree. Yes, because it is having at most two children. We can call it also binary tree because it is having two children. Now let's see another example. 1 2 3, and again it's having two children 4 5. Again it's having 6 7, and let's say we're having 8 children. So the question is, can we call it a binary tree? Can we call it a binary tree? So what is the answer? We cannot call it a binary tree. This is not a binary tree. Why? Because observe here the descendant, that means next node. Descending nodes, that means descendant. Those child nodes, the number of child nodes is 3, but in binary tree the number of maximum child nodes is 2. So it is not a binary tree. Not a binary tree. Not a binary tree. So we all understood about the binary tree. Now next, understanding what is binary search tree or BST. So understood the binary tree. Now we'll be understanding the binary search tree or BST. So binary search tree is a very important term in programming, because if we move to solve LeetCode questions or other type of platforms what are available HackerRank, if you solve data structure question, you get this term binary search tree, BST. So the term binary search tree, that means they are having something like balanced. Let's pause this tree. 10. This is 10. So this 10 is the root node. Now we are inserting 5 here. Just observe, we inserted 5. This is 5. And again we are inserting a node here, 12. This is on the right side. Now again we are inserting an element here, that is 2. And we inserted the element 3 in that side, or 6. So observe the tree here. Just notice one thing here. Whenever you will be noticing one thing here, that if you observe that tree, this is having at most two children. This is having at most two children. At most two children. So this is a binary tree. At most two children. At most two children. As it is having at most two children, that's why it's a binary tree. Now one important things to notice here. Look, just observe. Just observe, this is the left part. This is the left part and that is the right part. So if you observe the left part, if you observe the elements of left part, what are the elements? These are 5, 2, 6. And notice the root node is 10. So all the elements that are available in the left side, these are lesser than 10. And all the elements in the right side, those are greater than 10, 12, 13. These are greater than 10. So binary search tree means a tree in which the lesser lesser nodes, lesser value, node value, which node value is lesser than this binary root. These are stored in that side, and the greater value are stored in right side. That is called binary tree. Now observe this subtree, this subtree, this section. If you observe this section also, you can observe the two. The lesser value is stored in that side, and the greater value than this root node is stored in that side. That means this is also binary tree, binary search tree, because it's following all the principles of BST. So this type of tree, whenever we get, we call that binary search tree. Okay, we understood the binary search tree. The next term, balance tree. So a tree where the height of the left and right subtree of every node differ by at most 1. That means if we get a tree where the difference. Now again, let's take our tree for balance tree. Now we'll be understanding the balance tree. Okay, balanced tree. Balanced tree. So let's take our example 10, 5, 2, 6, 12, 11, 13. So this is also a tree, but the drawing is not good. 11 and 13. So if you observe the tree, we can also take more elements, like here we can take 12.5, and here we can take 14. So if we observe this tree, if you observe the left tree and the right tree, so this side we call this side the left tree, and the right side we call it the right tree. So this side is called the right tree. So if we just observe this tree, so if we just observe this tree, we can see the height difference. Notice, look, this is the height. We always start the count, we always start the measurement of height from the ground. So we will be starting measure. So this is the height 0. This is height 0 of the right side, and this is height 1. That is height 1 of the left side. This is left side. So if we just count the difference, height of right minus height of left, what the difference we will get, that is height of right is right now what, this is 0, that is 0. So we'll take the mod value, that is 0, and the left, that is 1. So the mod value comes to be 1. We got the mod value to be 1. So at this level we get that these are balanced, because the principle of balance is they can have the at most 1 height difference. So if you again observe from this n equals to 1 to this level, n equals to 2, if you again observe, we can see the difference, and for this node at this level we just observe, so there is only 0. So in that type of tree where the height difference is 1, we call that balanced tree. So we understood the balanced tree. Now we'll be talking about the complete binary tree. बात बात बोलता हूँ यार. Complete binary tree. Complete binary tree. Full binary tree. First I say complete binary. Strict binary tree. Complete binary tree. Complete binary tree. Other than this, has 2 children. So now we'll be observing the full binary tree. Full binary tree. So what it tells, a binary tree in which every node other than the leaves has 2 children. That means without the leaves, every node should have at least binary tree tells that a binary tree in which all levels are completely filled except possibly the last level. That means all levels are filled except the last levels, and which is filled from right to left side, which is filled from left to right side, not right to left, left to right side. So that is called complete binary tree. So we'll be understanding the complete binary tree right now. Complete binary tree. So the first condition of complete binary tree, that it should be filled. It should be filled from right. It should be filled except the last level. it should be filled except the last label. The number one criteria was it should be filled except the last label, except the last label. That was the number one criteria. And the number two, second criteria was it should be filled from the left to the right side. It should always be filled from left to right side, left to right side. That means the element initialization should be left to right side. So suppose let's take example. This is element 1 and then this is element 2 we took the elements from right side. Now 3, now we take 4, now we take 6, and then we take 7. So this is the insertion of elements. Now we also take additional elements like 8 and now 9. So notice this tree here, the insertion order. First we inserted the elements 1. Then from left side to right side we inserted 2, then 3. Then from left to right then we inserted 4, 5, 6, 7. And then from 8 to 9. So every time we inserted, the insertion order was same, left to right. That was the strict insertion order that we inserted from left to right side. And the most important second factor is that, and the second factor that is that we only the last level. This is the last level. That is called the last level. So only the last level is incomplete. That means all other levels should be completed. So in that type of tree, we call this type of tree as complete binary tree. Okay, so we understood the complete binary tree. Now we'll be observing the full binary tree or perfect binary tree. So the full and perfect binary tree are same tree. That means the name are different, but full and perfect binary tree have the same criteria. So let's observe full or perfect binary tree. Full or perfect binary tree. So the condition of full and perfect binary tree that all the nodes should have complete children. That means it should have 2 children for all nodes and the children level should be at the same level. That means suppose let's write the first condition, must have 2 children. Must have 2 children. Must have 2 children. This is the first condition to become full or perfect binary tree, and the second condition is children level should be same. Children level should be same. Children level should be same. So now let's see an example. So let's say this is 1, this is 2, this is 3. So if we call this, now look, this is the parent node, this is the root node, and these are the child nodes. So all the child nodes they are at the same level. So we have to maintain the same level, and the root node should have 2 children. So this is a full binary tree. We can call it that this is a full or perfect binary tree. This is called a full or perfect binary tree. So suppose if you take more example like this, 4, 5. Now the question is that a full or perfect binary tree? No, that is not a full or perfect binary tree. Why? Because the level is not same. Look the left tree, the left level is 0th level. This is the 0th level, that is 0th level. Now this is first level and that is second level. So if you notice the level of left side level is second level, and the level of right side is still at the first level. So the level is not matching, they are not the same. That's why this is not a full or perfect binary tree. That means the level must be same. So if you insert more elements like 6, 7, now they are at the same level, and now again we can call them full or perfect binary tree. So this is a full or perfect binary tree. So okay, we understood all the type of trees. There is also one more tree that is called strict binary tree. So let's understand the strict binary tree with example. So we'll be understanding the strict binary tree here. So let me just remove those things is to here. Okay. So now we'll be understanding the strict binary tree. Strict binary tree. So the condition of a strict binary tree is that either it should have 2 children or 0 children. That means either the nodes will have 2 children or 0 children. So if we see any type of tree that is having either 2 children or 0 children, then we can call it strict binary tree. So suppose again we are observing the same example. 1, 2, 3 and 4, 5. Now notice this one, this example. If you notice from here, it is strictly having two children. It's having two children, and the children are 2 and 3. The children of 1 is 2 and 3. And if you notice from this 2 here also, the children of 2 is 4 and 5. So this 1 and 2 are strictly having two childs. Those are having two childs. But if you observe 3, this is not having childs, and this is strictly 0 childs. So the condition that strict binary tree is that node should have 0 or 2 children. So it's satisfying 2 children or 0 children. So we can call it strict binary tree. Now let's take an example. If we just insert one element 4, 5, 6. So can we call it a binary tree? No, we cannot call it a strict binary tree because here cannot be two nodes. Here must be either empty node or it should have two nodes. One node, it cannot be strict binary tree, then it will move to the condition of complete binary tree. So this is the concept of strict binary tree. Now we understood all about binary tree, so we made it a strict binary tree. So now we'll be understanding the level concept. There is one more concept, what is called level. I mean the number of nodes at what level. So we'll be understanding that concept. For that we'll take a binary tree. And okay, so now we'll be understanding the number of nodes at every level. So for that we'll start with one single node. So suppose now we have a tree with only one node. This is our tree with only one node. So what is the level of this one single node? The level is, this is the 0th level, so we call it at 0th level. So the number of nodes at level, this is 1. Only one node is present at 0th level, so we can call it 2 to the power 0. Now look, this level we are representing this as I, so this is the level moved to here 2 to the power 0 in the power. Now we are taking second example. This is tree and this one. These are the nodes. These are the nodes. So if you observe in the second level, that was level 1, this is level 2. So how many at level 2, how many number of nodes there is? At level 2, the number of nodes is 1, 2. So there is 2 nodes. If we just make it more larger tree, this one, and we're adding more nodes, this. So now if we just number level 1, level 2, and this is level 3. So at level 3, how many nodes are present? 1, 2, 3, 4. So this is 4. Now look, do the generalization. This is 2 to the power 1, this is 2 to the power 2. Sorry, I just make a mistake here. So the level counting starts from 0, and then this is 1. Again, that is 0 level, 1 level, and second level. So this will be 1 and that will be 2. So now observe, this level is coming to the power. So from there we can conclude that number of nodes at any level, is that power. That will be 2 to the power of that number of level. That means number of nodes at any level. So number of nodes at any level, number of maximum nodes at any level, number of maximum nodes at any level, that is equals to 2 to the power I, because every time this ith value comes here, 2 to the power 0, 0, 2 to the power 1, 1, 2 to the power 2. So at any, for any number of i's value, that will be 2 to the power I. So this is the maximum number of nodes. Now what can be the total number of nodes in a tree? Total number of nodes in a tree. So to find the total number of nodes, we have to add all the nodes of all level. So at 0th level, the number of nodes were 2 to the power 0. Next level, the number of nodes were 2 to the power 1. And after that, the number of nodes were 2 square dot 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 dot. So for nth level, the number of nodes will be 2 to the power n. So the formula from geometric series, that is a into r to the power n minus 1 by r minus 1. So the value of a, this is 1. 2 to the power 0, 1. R to the power n, this is r, this is n minus 1. Notice we didn't keep this n. We have to put the value of n, r to the power n minus 1 by r, 2 minus 1. So here what is the value of n? Now try to understand. Try to understand the value of n. If we just notice, it starts from 0, and if we just notice from 1 to n, this value is already n and this value is 1. So the total number of values in here, this n, that is n plus 1. So that will be n plus 1 minus 1. So the maximum number of children that is possible that is 2 to the power n plus 1 minus 1. So this is the maximum number of nodes that can be possible in a tree. So that's all about tree. We understood all the type of trees, all the classification of trees in details, not in short, just we saw all the diagram of trees. Then we understood the node level of the trees, that the maximum node at any level that can be 2 to the power I. Here I represent the level, and the level counting always starts from 0. That is conclusion. And the total number of nodes in a total tree, what will be the total number of maximum number of nodes? So the maximum number of nodes can be given by the formula 2 to the power n plus 1 minus 1, that is, so that will be the maximum number of nodes. From the GP series we got this. So in next video we'll be understanding the coding architecture, that how we can convert this into coding. So how we can convert, so if you talk in terms of coding, so we'll simply convert this one like this, its actual structure like this. So in next video we'll be understanding the actual structure, how we can convert this. So okay, meeting in the next video.